Welcome to another explainer. Okay, we are diving straight into this incredibly dense, highly mathematical 2026 paper by Dean Kulik called The Recursive Edge. And let me tell you, what we are looking at today isn't just some incremental update to artificial intelligence. No, this is a fundamental redefinition of how computation models reality. We're going to explore this incredible synthesis of adaptive spline architectures and agentic paradigms that are quite literally overturning everything we thought we knew about machine learning.
To map out this massive paradigm shift, we'll cover 1. The structural turn, 2. KN and splines on the edge, 3. Curing context rot, 4. The Nexus Mirror, and finally, 5. Realigning AI with reality.
Section 1. The structural turn, moving beyond the depth hypothesis.
So, for nearly a decade, the AI industry relied really heavily on what's called the depth hypothesis. This was basically the assumption that you could just brute force complexity by stacking endless layers of fixed, static nodes. It was an era all about scaling up sheer size, using the multi-layer perceptron as the baseline atomic unit. But the structural turn completely abandons that brute force approach. Instead of forcing intelligence into those static nodes, it completely shifts the focus to the mathematical quality of the connections themselves. We are moving away from deep, rigid networks into systems defined by dynamic, highly mathematical edges. It is a total game changer.
Section 2. CANs, splines on the edge.
This brings us to the micro-level changes that fundamentally alter where the actual thinking in an AI happens. Enter Kolmogorov-Arnold Networks, or CANs. This architecture does something truly radical. It actually takes the learnable nonlinearities away from the neurons and relocates them directly to the edges. Instead of using static single numbers for weights, CANs turn the connections themselves into adaptive mathematical functions. Specifically, they parameterize these weights as univariate B-spline functions. And theoretically, this local plasticity solves one of the biggest, most frustrating headaches in machine learning: catastrophic forgetting and low-dimensional manifolds. And the mathematical formulation of these univariate B-splines is fascinating because it brings the rigorous framework of the Kolmogorov-Arnold representation theorem, which is originally from all the way back in 1957, to life in these 2026 AI models. It shows exactly how those old, clunky global weights are completely rejected in favor of these local additive spline functions. So the network is no longer a rigid web. It's this flexible mathematical curve that is adapting at every single connection point.
Building right on top of that theorem is the Cox-de Boor recursion formula. This is the actual math that makes those B-splines work on the network's edges. By relying on this very specific recursive math, CANs achieve that local plasticity we just mentioned. Basically, this means the AI can learn new information and adapt its edges locally without completely overwriting and destroying the broader patterns it already learned. It is a structurally sound, reliable path to memory and continuous learning.
Section 3. Curing context rot.
Now, just as CANs rejected massive global weights in favor of local splines, we're seeing a parallel revolution over in natural language processing. Recursive Language Models, or RLMs, reject dense, massive global context windows. You know how traditional models try to hold massive amounts of text in a fixed window? Well, that leads to context rot, where the AI just slowly loses track of information. It forgets what it just read. RLMs fix this by replacing it with local, iterative, agentic loops. They redefine context not as a static, dead block of text, but as a dynamic, interactive environment.
The mathematical implications of this shift are honestly staggering. By moving from a static global context window to this interactive recursion, the model dramatically reduces its complexity burden. It goes from an exponential nightmare, big O of n squared, straight down to a constant size of big O of 1. That is huge. The effective context window seen by the attention mechanism just becomes constant. It's just the size of the current chunk plus its state. So what does this actually mean for us? It simply means we stop trying to shove an entire book into an AI's working memory all at the exact same time. Instead, complexity is officially offloaded from the architecture's width, meaning how much it can hold at once, to the inference time, which is the number of recursive steps it takes. We are finally allowing the AI to read, synthesize, and recurse, which, if you think about it, is exactly how human reasoning works.
Section 4. The Nexus Mirror.
This brings us to a really deep theoretical symmetry between those spatial changes we saw in CANs and the temporal changes in RLMs. It's captured perfectly by this insight from the author. Intelligence scales better when interactions are sparsified.
either spatially via splines or temporally via recursion. Both of these architectures are direct responses to the massive inefficiency of dense, global interactions. But the Nexus Mirror framework proposes something even deeper. It suggests that these 2026 architectures aren't just clever computational tricks to save time. They actually mirror the fundamental causal and physical structures of reality itself.
When you compare the attention mechanism formula directly to Newtonian physics, like force equals mass times acceleration, a really distinct pattern emerges. By constraining the network to sums of univariate functions, CANs act as a true mirror to natural laws. This structural prior actually explains a major breakthrough we've seen in AI plus science tasks. Because the network structure mathematically aligns with causality, these models are suddenly able to independently discover physical formulas, like the Navier-Stokes equations for fluid dynamics, directly from raw data, no human prompting required. And this structural prior extends even to Einstein's mass-energy equivalence. The AI isn't just curving a line to clumsily fit a spread of data points anymore, it is actively finding the foundational, causal formulas of reality. Why? Because its own mathematical structure, its use of splines and recursive folding, finally aligns with the physics of the universe. It doesn't just fit the data, it organically finds the formula.
Section 5. Realigning AI with reality.
This total structural realignment forces us to reconsider the baseline geometry of what computation actually is. The source material dives into what it calls an ontological inversion. It argues that our traditional view of reality, as an empty void where objects transition through space, is entirely backward. Under this pure domain architecture, existence is defined by a perfectly filled topological frame with absolutely no empty storage slots. What we perceive as motion or transition is actually a continuous projection shift of an invariant structure. Under this lens, an electron isn't a static noun, it's a frozen verb, a persistent loop of computational operations utilizing recursive rotation to maintain stable identity. Reality itself is unbounded recursive computation. Mind-blowing, right?
So to summarize our explainer today, we really have witnessed a total paradigm shift. 2026 marks the definitive end of the deep learning brute force era. We've shifted away from the depth hypothesis over to the structural hypothesis. We are seeing spatial sparsification through CANs, which are completely redesigning network weights, and temporal sparsification through RLMs, which are redefining context. Ultimately, we are moving toward intelligent systems that are structurally matched to the modular, causal nature of the physical universe itself. I want to leave you with that provocative thought. If our AI architectures are now structurally aligned with the very physics of reality, are we merely computing the world, or through the Nexus Mirror, are we finally reflecting it? Thank you so much for joining me to explore this incredible paper, and as always, keep questioning the structures around you.